Okay. No problems with saving that last week, Jess?
With what?
Did you have any problems saving the one we did last week?
I think it was Jellin who did last week.
Okay.
I don't know.
We won't worry about that now. Okay, well, I'll share my screen. And there's the notes that I have sent you. So can you see those okay? All right. Economy cycles. I don't know whether you've had anything to do with an economy cycle yet. Have you? Do you know what that is?
I've heard of it, but I haven't personally done one.
Okay, so, well, let me just read through this and I'll explain it as we go along. An economy cycle is a requirement of the NCC, Volume 1, Part J6D3C, depending on the applicable climate zone and the system airflow rate. NCC, that's the total supply airflow rate, the system airflow rate. NCC table J6D3 sets out the climate zones and the airflow rates which apply to this requirement. So, for example, Melbourne is located in climate zone 6, so that an air conditioning system with an airflow rate greater than 2,000 litres a second must be provided with an economy cycle. So just to show you the NCC, so J6D3C, and if I can highlight that, no, I can't. So C, an air conditioning system which provides the required mechanical ventilation, so which means it's bringing in outside air as well, other than in climate zone 1, or where dehumidification control is needed. So if you need special, like in a laboratory, for instance, you may have dehumidification control, or a hospital area, then that doesn't apply. But generally, for a general commercial air conditioning system, it must have an outdoor air economy cycle if the total airflow rate of any airside component of an air conditioning system is greater than or equal to the flow rates in table J6D3, which is down here, J6D3. So these are the climate zones and the applicable flow rates. Melbourne's climate zone 6, and that's the one you're probably mostly going to be concerned with. But if you're doing a job in Sydney, for instance, that will be a different flow rate. So if you have a flow rate greater than 2,000, you must have an economy cycle. Basically, an economy cycle, well, let me read through this. The function of an economy cycle is to use outside air for cooling a space rather than refrigeration when the outdoor air conditions of temperature and relative humidity are suitable. So in other words, the way the system is, so I tried to find a schematic, but I couldn't find one. And I'm not very good at drawing things. But it's, so in your air conditioning system, you've got a supply air duct, you've got a return air duct, and you've got an outside air duct, okay? So in the return air duct and outside air duct, you have motorised dampers if you're going to have an economy cycle. And when you're changing over to economy cycle, the return air damper will close, the outside air damper will open, and you'll be using outside air for cooling rather than the air conditioning refrigeration system, or if it's a chilled water system, rather than using chilled water. So let's say if the outside air temperature in Melbourne is 17 degrees, say, or less, then you can turn off or shut the return air damper, open up the outside air, turn off the refrigeration, and just use the outside air for cooling. So you're getting a whole lot of fresh air, and it's providing the cooling. So that's what I've said in the next sentence, basically. Where you have an on-off sort of situation, the outside air damper opens, the return air damper closes, that's basically, well, it's an on-off economy cycle. It's either on or it's off, okay? At that set temperature, it starts. When the temperature rises to whatever you determine is the right level, let's say 19 degrees, it turns off again and you go back to the normal cycle. You can also have a modulating economy cycle where the outside air and return air dampers modulate as the conditions change. So you're still getting, rather than just shutting it off, you're still getting the economy of additional outside air up to a point where it's no longer a benefit to use outside air for cooling. Does that make sense?
Yeah.
So it's like opening your window. If it's nice and cool outside, but the sun's shining, you let some fresh air in, you get some cooling. So that's all it is, and it's saving on refrigeration during that period. Now, if an economy cycle is not required by the NCC, in other words, if your airflow rate is less than those values given against the climate zone, you can still provide an economy cycle. There's no reason why you can't do it, but there's a bit of cost involved because you've got the motorised dampers, you've got the control system, and the outdoor air sensing and so on to get it to operate. So you're looking at several $1,000s for that facility. So generally, people don't do it unless you have to by the NCC. Now, the other important thing is relief. So if you're operating an economy cycle, suddenly you've got a lot more fresh air coming into the building or outside air coming in, which is going to pressurise the building. So you have to provide some form of relief. And we've talked about relief before, balancing rooms, balancing floors, balancing the whole system. So it's the same thing. So there's a number of ways that you can do it. You can have motorised dampers and relief cowls. So you might have if it's just a single story building, put a cowl on the roof with a motorised damper and some ductwork. And while you've got economy cycle operating, open up the damper and let the air be pushed out. Or you can have motorised dampers and wall-mounted louvers, same principle, but if it's multi-story, you could have louvers on the walls, motorised dampers and let the air go out through the wall. Or you might put in exhaust ductwork with fans and motorised dampers as well. So you haven't, sounds like you haven't actually come across one. So it's something that you will see quite often. So I thought it was worth mentioning, and just without going into a whole lot of detail, that's what it is. So any questions on that part?
Why would you need a exhaust fan if you've got couldn't you just rely on the pressure of putting that volume of air into relieve there?
But it depends where you're going to relieve to. So if you've got a situation where you have to, or you can't relieve directly through a roof or through a wall, or you haven't got any other relief path that's nearby the space that you're air conditioning, then you might have to run ductwork out through the building to a point where you can actually exhaust the air to the outside. And obviously there's going to be some restriction in the ductwork if you do that. So you just might need a fan.
Right.
Yeah. I mean, if you work out that the pressure that you develop by the economy cycle is enough to push the air out through ductwork without a fan, don't put one in. But it's just, don't overlook that possibility. But relief is extremely important, because if you don't have relief, it's not going to work properly, which is the same in all these situations of balancing.
I have a question before we move on. The economy cycle is operational all year round, so it doesn't matter what the temperature is like outside, or does it take that into account?
Yeah, it's operational all the time. Well, it's available all the time.
Right. So
but go on.
I was going to say, so you have to account for the temperature of the air, the outside air coming in.
Yes. So you have outside air sensors. Normally these days you'd have a BMS, building monitoring system, or BMCS, building monitoring and control system, which has outdoor air sensors, which is normally temperature and humidity. And you have the same on the inside, and they're just comparing all the time, so that it's computer controlled. So it's looking at the indoor temperature, looking at the outdoor temperature. When it gets to a point, and there'll be a set point which you set up when you're commissioning the system, where you say if it's well, either two ways you can do it. Either it's a temperature difference. So if you're looking at outside, if your inside temperature is say 24, and then you might set the outside temperature to 17, like I said before. These things are adjustable, so you can work out what's the most suitable. But at 17 degrees, the economy cycle, or 17 or below, the economy cycle will be operational. If you're cooling, if you've got a cooling signal inside, try and give you an example to make it a bit clearer. Say an office building, which is fully occupied, and because it's got lights on and there's people in there and there might be some sun shining outside. So it's actually, even though it might be cool outside, and this is typical in Melbourne actually, this happens quite a bit down there. You've got a nice sunny morning, but it's cold outside. And say it's 13, 14 degrees. If you're sitting in an office which is fully occupied, you've got computers on, people are in there, lights are on, without air conditioning, it can get very hot in the office, even though it's cold outside. So in that situation, instead of running the refrigeration for the air conditioning to cool the space, outside air is ideal. So you can just bring outside air in. Obviously, there's a point where the outside air might be too cold. So you probably need a band there where you say between maybe 13 or 12 and 17 degrees, outside air is ideal. But these things are all adjustable through the control system. So once the economy cycle is operating, it's monitoring the indoor conditions as well. And so it's trying to maintain, say, 20, well, if it's winter time, it's probably trying to maintain about 21 degrees inside, 21 or 22 degrees. So it's looking at that. It's using the outside air to provide the cooling that you need for the space. But if it's starting to get too cold, then it's going to either close the economy damper or close the outside air damper and go back to a normal cycle. Or if you've got a modulating system, it will start to modulate the outside air. So instead of having the full supply air coming through the outside air, you might modulate back to say 50% or something. And the control system is doing all these things all the time, comparing outside, inside temperatures and working to maintain the inside temperature, the inside design temperature, but getting the economy of using outside air as much as possible.
So I've got two follow-up questions. One, why is the flow rate set 2,000 liters per second? Like, why not 100 or 500 or?
Oh well, that's a really good question. The only one who can answer that is probably the person who wrote that part of the NCC.
Yeah.
Back in the days before the NCC came into existence, and probably even in the early days of the NCC, there was no actual notation of that. It was more a design decision. So I started my career in Melbourne, and I worked with my first job was with consulting engineers, and we worked on big projects. And we would always have this debate about whether we should have an economy cycle or not. And if it's a large enough building, the answer would always be yes, because even 40 years ago, we were very conscious about energy consumption, and an economy cycle can provide very big savings by not running the refrigeration when you don't need to.
Right.
And
so, but when I was going to say, when it's hot, this is my second question. So when it's hot outside, could it potentially cost more to cool a space if you're using an economy cycle?
If it's hot outside, the economy cycle won't operate.
Right. Okay.
It's looking at the outside air temperature. It's like I said, it's probably got to be 17 or less.
Mhm.
Okay, if it's above 17, it just won't operate.
Okay.
You'll
Yeah. I'm with you now.
you'll operate on minimum outside air for all that time that's above the set point. The other control option is to use enthalpy, which is looking at temperature and relative humidity and comparing and having the same on both sides. So inside you've got temperature sensors and relative humidity sensors and the same on the outside. And they're actually doing a calculation to work out what is the enthalpy of the air inside and what is it outside. And so that's in theory an even more energy efficient way of doing it. If the outside air enthalpy is less than inside, then use outside air until the enthalpy is greater outside than it is inside.
Right. Okay. That makes sense.
Have you
So
ever seen an economy cycle used for heating, Peter? Like in summer, underground heating or something?
sorry, I missed the start of that, Jess. Could you say it again?
Have you ever seen an economy cycle used for heating, like what Jordan was asking? Like
For
using
heat,
the
what to
warmer
use
to
hot
bring hot,
outside.
yeah, to bring hot outside air in, like to an underground space or something where it's
Oh,
cooler.
the simple answer is no, I haven't seen it, but I suppose if you've got a space that's always cold and you need to heat it, and the outside air is going to be hot, you could do it for sure. Um, like, yeah, I suppose it's possible, but no, I've never seen it done.
Mhm.
It's pretty unusual. But if you're aware of it, if you're doing a project that's got a space inside that is underground, you expect it to always be cold, and you want it to maintain a certain temperature, then you could do it. Yeah, why not? It'd be just kind of a reverse way of doing it. You'd be looking at the outside air temperature, and when it's hot enough, start using that. But if it's cold outside, well, you wouldn't use it. You'd have to use your heating system. Does that answer your questions, or
Yeah. Yeah.
do we?
Makes sense.
Okay. Um, so that's that's that part. Now, energy recovery ventilators. Have you come across these at all yet?
Heard of them?
Okay. Have you
I don't think
used them, Jess?
I've also heard of them.
Right. Okay. So again, it will be part of what you do at some point. It's probably not. It's not going to be in every job, but it's quite commonly done. Energy recovery ventilators, ERV for short, are air-to-air heat exchangers, which pre-cool or preheat incoming outside air by heat exchange with the exhausted room air. The heat exchangers are typically either plate type or a rotary heat wheel and can provide either sensible only or sensible and latent, which is enthalpy heat exchange. The rotary heat wheels are very expensive, very generally quite large and used on, well, I mean, you can get small ones. You can use them on a laboratory project or something where it's more critical, but generally the ones that you'll come across are the plate type. I'll show you a picture of some just so you get an idea of what we're talking about. So this is Armcore, which is one of the Australian companies that make them. That's what it looks like, but if you look at the schematic, so you've got fresh air or outside air coming in. There's two ports that you can use there, and then return air from the space, which has already been conditioned, comes through and exchanges heat with the outside air. So if the outside air, which is shown red, if it's hot, and the return air is at room temperature, the heat exchange occurs there, and the supply air is cooled or pre-cooled and delivered to the space, and the exhaust air, which is obviously picked up the heat from the outside air, is exhausted out. So that's the typical process. And in this diagram, there's lots of options, but it's only to do with the ports available. So you'd only use one port for each airstream. But there are other ports available if it's more convenient for the configuration of the space. That's basically what it looks like. It's just a box with all these ports on it. And inside there's I don't know if there's a picture of the heat exchanger itself. Oh no, there's not. It's just a fabric. You can't really see it there. Anyway, this table shows you the air quantities that are available in these compact style. So from 125 litres a second of outside air up to 1225. Up to 625 litres a second, the height of that unit is 440 millimetres. So that could probably fit in a ceiling space normally. But then above that, they get quite a bit bigger. So you probably would have to put them in a plant room or outside the space. The outside air heat load can be significant, as you're well aware now, having done some camel heat load calcs. The outside air is quite a dominant heat load for both, whether it's heating or cooling. And it's, particularly in summer and winter. The ERV serves to reduce the heat load and provides some energy savings by reducing the outside air heat load. Potentially could reduce the air conditioning equipment capacity and cost. So if you're preconditioning, basically these are preconditioning the outside air. And if you're doing a camel heat load, there is a tab in there that asks you, is there a preconditioner? Have you come across that?
Yeah.
Yeah.
So this is what we're talking about. An ERV is a preconditioner. And so by having that there, you're reducing the outside air load, and you potentially can reduce the size of the air conditioning equipment, and obviously the cost, and it reduces the operating costs. So once again, the NCC specifies requirements for these systems, for energy reclaiming systems, or demand control ventilation. Excuse me. We're specified in table J6D4 based on the climate zone of the project and the outside air flow rate. Outside air flow rate can be controlled by modulating control, which is, for example, CO2 sensing, or using an ERV. So have you come across CO2 sensing at this point?
I've heard of it.
Okay,
Yeah, I've
so
just seen it. Yeah.
sorry, Jordan, what was that?
I was just saying, I've just seen it in, like drafting,
On drawings,
like
yeah.
Revit and drawings, yeah.
So how that works, this is quite an historic thing, I would say. I mean, ever since I started work, which was a long time ago, back in 1980, outside air has always been an issue as to how it affects the heat load. So we've always been looking for ways to mitigate that load. And CO2 sensing is relatively new. Economy cycles have been around since I started work. ERVs, well, they have in a way. We used to use heat wheels for exchanging heat with the outside air. Right back in 1980, we were doing that, and that's been around for a long time. But the ERV itself is probably relatively recent. In the last, say, 20 years, they've come in. But prior to that, people used to use all sorts of funny ways of trying to control the outside air flow rate. Like for a bar, for instance, a bar could go from 0 people to 200 people, at a certain time of day. And if it's in the afternoon, and it's a hot day, you know, you need a lot of outside air to comply with the standards at that time of day. So one of the early things that people used to do is have a switch behind the bar where they could select roughly how many people were in the bar at the time. I mean, it's pretty crude, but if there's only, say, 50 people in the bar, they could go in there and switch the outside air damper to a certain level to reduce the outside air coming in, because you don't need it for that many people. But we have got a bit more sophisticated since those days, and now with ERVs, you can either get the benefit of the heat exchange, but with CO2, as I said, that's probably been around for, well, it's been around for quite a long time, but it's now being used more widely. It looks at the carbon dioxide concentration in the space and compares it with the carbon dioxide concentration outside. And well, the main thing is to maintain the concentration inside below a threshold, which is around 800 parts per million or less. So as long as the CO2 in the space concentration is less than that, then you can reduce the outside air flow rate. So that's what CO2 control is about. So there's an energy saving benefit from that, because you're not bringing in so much outside air during, you know, hot times and any time. Just go back to the NCC and I'll point out the relevant part here. So now we're talking about mechanical ventilation system control. Part B, when serving a conditioned space, except in periods when evaporative cooling is being used, which is not very often, where specified in table J6D4, have an energy reclaiming system that preconditions outdoor air at a minimum sensible heat transfer effectiveness of 60%. So generally the 60% is a practical figure, which is about the best you get with these units. So 60% of the heat in the outside air is removed in the process, in the heat exchange process. Does that make sense? And you can get this technical data from the manufacturers. They can tell you exactly what the efficiency of these units is. Now, so A is ERV or demand control ventilation in accordance with AS 1668 Part 2, if appropriate to the application. And then there's a couple of things to bear in mind. Not exceed the outdoor air quantity required by Part F6 by more than 20%. So again, this is an energy efficiency thing. You don't want to have too much outside air because that will create additional load, and it can affect air handling units and fan coil units. We won't go into that at the moment, but it will affect the performance of those units. So except where additional unconditioned outside air is supplied for free cooling, so that's the economy cycle. So that's obviously got to be an exception, because if you choose to use an economy cycle, obviously you're getting energy efficiency by doing that. Or additional mechanical ventilation is needed to balance the required exhaust or process exhaust. So this is getting back to the balance again. If you need additional outside air to make up for toilet exhausts and whatever other spaces you have in there that have to have exhaust, it's got to come from somewhere. And so if you need that additional makeup, it's probably going to come from outside air if you haven't got adjacent spaces that you can get it from. Or an energy reclaiming system preconditions all the outdoor air. So that's another not disclaimer, but option. So does that make sense so far?
Yeah.
Okay. Sorry. So just going back to this. So that refers to that table, J6D4. So climate zone, outdoor air flow, required measure. So let's look at Melbourne. Climate zone 4 and 6. If the outside air flow rate is greater than 500 litres a second, we have to have either modulating control, which is demand control ventilation, CO2 control, for instance, or energy reclaiming system. So you have to have it if your outside air flow rate is greater than 500. Now, there's an obvious question here. Does anything come to mind? Well, you haven't done it, so I'll tell you what the obvious question probably would be. What if you have a whole bunch of fan coil units in a space and you've got a common outside air system which delivers more than 500 litres a second, but it's distributed to all those fan coil units. So each one might be getting, let's say, 50 litres a second or something like that. Do we have to have an ERV? And this is debatable because it's not really clarified in NCC. And I know that Philip and Ivan and the guys have talked about this. Do we have to have it? My view is no, you don't in that situation. But if you've only got one fan coil unit and it's delivering more than 500 litres a second in Melbourne, then you do have to have it. Well, you either have to have an ERV or CO2 control on the outside air. So does that make sense?
Yeah.
Yeah. I'm working on a job at the moment where this scenario, they have preconditioners because they've got like 5 air handling units or fan coil units in a space,
Mm-hmm.
and they precondition. I can share my screen for a moment.
Yep.
They've got like this big open plan training area. And here they've got these 2 units in the middle.
Oh, yeah.
It's actually maybe this is different actually because they're serving outdoor air directly to directly to the space. They're not serving it to the
yes,
units.
okay.
That may be
Okay.
different.
So that's another application anyway.
Although here actually there is.
Oh, yeah, that's going to the unit there.
Yeah.
I mean, if you're going to put one in, it makes sense to size it so that you can feed fan coil units as well. I suppose the first question is, do you have to have one for the air conditioning systems? It makes sense if you've got enough air. You've got to have enough return air or relief air that you can lose to outside, that you can exhaust out of the building to exchange heat with the incoming outside air. If you don't, there's a number of ways of looking at it.
Yeah.
So what have we got there?
I think this is what the space I was thinking of. I think they actually don't precondition the outdoor air. They've just got a fan that pulls it in from outside.
Right. So
this part,
what's the flow rate of the outside air there?
it's
On the fan there, I noticed if you go up to
80. Yeah.
oh, it's only 80 litres a second.
Oh,
yeah,
sorry,
so,
no, 180. So 80 is the diffuser and 180.
and this is in Melbourne.
It's in Brisbane.
Oh, okay. So that's a different climate zone. But then you don't use economy cycles in Brisbane that much because it's generally quite a bit warmer than in Melbourne.
Yeah.
So they're not as effective or energy efficient really because it's not cold enough. Yeah. So, but that first that drawing there. So they're supplying preconditioned air to a space. Is that space just ventilated that it's serving, or what is that space there?
I think it's like, it looks like toilets. I think it's like Yeah, toilet floors.
So it's make-up air to toilets.
Yeah.
Okay, and what they're doing is instead of using the room air to make up directly to the toilets, they're taking that through the ERV and exhausting it outside to get the heat exchange with the outside air coming in.
Is
I
that
suppose
ERV? It
is
looks
that
like here they've got a unit preconditioning it.
the ERV.
I don't know if there is an ERV. It looks like this is some sort of like
It's a
air
fan
conditioning
coil.
unit. Yeah.
Fan coil unit, is it? Oh, okay. Well,
Yeah.
that's operating on full outside air though.
Yeah.
Is it? Oh, okay. Well, that might be a special. Is this what sort of system is it? VRF, is it?
Yeah.
Okay. You can get with the main manufacturers like Mitsubishi and Daikin and probably some of the others. You can get special fan coil units designed to just operate on fresh air or outside air. The standard units won't function on 100% outside air, but these special units will. And they just deliver a lower airflow rate, and they can perform okay. Okay, so they're not actually ERVs, those units.
Yeah.
No, they're not. Otherwise, they'd have four connections to them. They'd have,
They don't, yeah. They just pull out outside air units.
yeah. Sorry, I should have picked that up before. It's a bit smaller. Takes a moment for me to sort of get with it on that drawing, but yeah, okay. Well, anyway, that's another option, but that's to have an outdoor air, a special outdoor air conditioning unit to precondition outside air is fine, but it's probably a bigger cost to install and to run than an ERV. And in actual fact, what was the airflow rate for those fan coil units?
Like we're in the vicinity of 600 meters a second.
But that's in Brisbane?
Yeah.
Okay, so what's the climate zone for Brisbane? Do you know?
I don't know off the top of my head.
Well, we can have a look because that would be interesting. Though I haven't.
It's zone 5. So I think it's, yeah, I think it's like 2,500 liters a second, according to your table that you showed.
But that's a ventilation system. Oh, yes, okay. So it's still it's serving a conditioned space, although it's toilet area. That's arguable as well. But so it's on climate zone 5, you think, is it? So it's greater than 1,000.
Oh, hang on, sorry, climate zone 2.
2. Okay.
2, yeah.
So if you go back to, sorry, I'll have to share my screen again. Go back to the NCC, climate zone 2, it's not applicable.
Okay.
That doesn't mean you can't use it. It just means you don't have to. So you don't have to use an ERV. So they've chosen not to use ERV. They've chosen to use a special outside air conditioner designed to run on 100% outside air, and that's fine. So that's probably, and it's within a VRF system, so it's a distributed system. It's probably the most sensible option, actually. So did we design that, or was that designed by a consultant?
Designed by consultant.
Okay. All right. Well, I think they've probably done the right thing there. But this is the process you have to go through. You know, where are we? What part of Australia are we in? What do we have to do? What's the best way of doing it? What's the most energy efficient? Or what's the if it's not governed by the NCC, what's the most economical way to do it? All right. Well, that was a good example, actually. What job in Brisbane is that?
It's a job in Rockley for a trading centre.
Yeah. Good. Oh, well, you're spreading your wings around a bit, getting around the country.
Yeah, that's it.
Okay, so where do we get up to? Yeah, so I've said here, Australian manufactured ERV units are available in a large range of sizes, from airflows around 125, which is the little one we looked at initially, up to 9,000 litres a second. So I've given a couple of websites there. These are both Australian companies, Armcore or Air Change. Air Change were really the pioneers, I suppose, in Australia of this stuff, but Armcore are a very good company, and we've worked a lot with them. So I'll just show you another. This is an Armcore one too, because they've got pretty good data to look at if you're looking for information. So these are the external mounted ERV units. These are for very big jobs, but that's an example of what they look like. And that blue part there is the heat exchanger, okay? And that's two connections. So one would be, say, fresh air, the other would be return air. It's the same schematic. There's a schematic again. Fresh air or outside air. We should call it outside air, not fresh air, because strictly speaking, how fresh is it? But and return air goes through the heat exchanger and you get exhaust and supply. And you can see the range of airflows there from as low as 300 litres a second up to 9,000. So you can get very large units. And these can be built into a packaged air conditioning unit with a refrigeration system or chilled water coils, heating water coils, bypass dampers. They can get very, very elaborate. Generally, the fans they use are EC plug fans. They can be speed controlled from the control system via a 0 to 10 volt DC signal. The large units, I say many of the ERV units are provided with integral filters. So those big units I just showed you would normally come with filters, particularly on the return air and the outside air, obviously, outside air and return air, to protect the heat exchanger from getting clogged up. And where filters aren't provided, a filter plenum is required external to the unit, which is quite common as well, to have to provide a filter plenum for those units. On the small units, I haven't seen any with filters on them. It's probably not a bad idea to put a filter on the incoming air at least, you know, to take out any dust or whatever's in the air outside. And I'll just put down a few options there that I just mentioned: chilled water and heating water coils, bypass dampers, economy cycle, refrigeration system. I was involved in a job in Brisbane, well, quite a few years ago, where they used units that came from overseas. I think they were made in France actually. They had everything in them. They had a refrigeration system. They had the ERV. They actually had heat wheels in them, so they were quite large units. It was for an IKEA actually, IKEA in Brisbane. Large store, very large package units, and they worked quite well. They were very energy efficient, and because we were operating on basically 100% outside air all the time. Again, because IKEA can have a very large occupancy at any time. So when you look at the design criteria for a project, and you look at AS 1668 Part 2 as to how many people you expect in that building, and if you've been to IKEA, you know what they're like. Sometimes they're just choppers with people. So you've got to provide outside air for all of them. So these units were 100% outside air, so they had all the bells and whistles that we've been talking about today. They were Lennox units, actually, I think. I think they came from France. So I've said there, packaged units are available for normal applications as well as for swimming pool applications, complete with ERV up to an outside airflow rates of 8,000. Now, they're the Australian-made ones. Overseas, they might be greater than that. And you might come across a big bulky store like say an IKEA or something like that, where you need a lot of outside air, but you've got to provide air conditioning. So this is an option to use these sorts of units. And when I mention swimming pool applications here, I mention that specifically because quite often you guys will do a pool air conditioning system. And pools, as you know, generally the larger pools have chlorine in them. Chlorine is very corrosive. So you have to be careful with the materials you use for ductwork, and anything that the air comes in contact with has got to be corrosion resistant. So these swimming pool packaged air conditioning units are made with stainless steel. So they can, they're resistant to the chemicals in the air. Just another thing to be aware of, and I'm sure you would be by now, the air pressure drop through the ERV can range from 100 up to 200 pascals, which is the pressure drop through the heat exchanger and the internals in the system. But that's part of the design of the system, and that's handled by the fans. But the fans also have to handle external static, which is the ductwork connecting to it. So you just need to make sure that when you're doing the design, the duct design, that you check what the allowable static is for the fans that are provided with the units and make sure that the ductwork works within that restriction. Yeah, ERV systems normally have 4 duct connections, which is what we looked at on the schematic. Outside air intake, supply air to the space, return air from the space, and exhaust. In this case, relief air or return air from the space exchanges heat with the incoming outside air and is exhausted to outside the building, which is that schematic that we looked at earlier. Basically, that's the principle. So that's pretty much it, really. I wanted to mention this because it will be relevant to you. It gives you a reference on where you can go and get information if you need it, and basically how they work. So on the outside of the building, you've got to have provision to bring the outside air in, and you've got to have provision for the exhaust air to go out. Okay, so if you have one of these ERVs, there'll be an additional louver or cowl or whatever it may be to let this exhaust air go out. The space between the exhaust air and fresh air is not really governed by AS 1668 Part 2. It is mentioned in that code that it's like an exemption, because it's not like you're exhausting toilet exhaust or something that might be a bit smelly or not good to bring back in. So it's just return air that's being exhausted out. So they can be. It's a good idea to keep these as far apart as you can, because one air stream is going to be potentially cooler or probably hotter. Anyway, try and separate them by as much as you can. But the table in AS 1668 Part 2 that talks about separation distances still applies here. So if it's up to 1,000, if it's 1,000 litres a second, it says 6 metres. So if you can achieve that, that's ideal. But if you can't, it's not critical. You know what I mean by that?
Yeah.
Because that table says if it's 200 litres a second, they only need to be a metre apart, even if it's toilet exhaust. So that applies. But I think what I'm trying to say is if it's 1,000 litres a second or more, 1668 Part 2 says 6 metres, but if you can't achieve it, it's not critical with this type of system. I hope that makes sense anyway. Any questions?
All clear.
Rightio. Next week I'm away. We're doing a quick trip to go and visit the family because this is probably our last chance before next year. So they'll be back the following week. So I'm just away for 1 week. Our next session, I'm going to share my screen. This is just a rough guide that I've been using. Can you see that spreadsheet?
Yeah.
So today we've talked about economy cycles and ERV. These are some of the topics that I've just put down as me thinking, and I've spoken to Philip and Ivan, and they've got no issues with it. But really, it's about you guys. I want to make it as relevant to you as possible. So if there's something that you want me to talk about, all you need to do is ask, and we'll do that. But these are topics that I thought sooner or later you're going to need to know a bit about. So we've got basic acoustics and vibration isolation. Now, you've already had some exposure to these things. Do you want to talk some more about that?
Sure.
So I've got notes that I can give you, and there's lots of references. This is quite a big topic, but we can do a bit of an introduction to it. So you've got an idea of what it's about and where to go looking for information if you need to. Then I've put down here fire rated duct. Again, this is something that you may need to know a bit about and where you have to use it. I'm sure you're familiar with fire compartments by now. Has that come up on any of your jobs?
Not for me, because I've not really been doing a lot of engineering stuff. So I was just going to suggest something else. As well as this, we could do both maybe. Depending on how Jess feels about it. Maybe going through some of the stuff that you're working on, Jess. I don't know if there's just to like kind of show what you're doing, because I literally have no exposure to any of the engineering stuff apart from like the heat load calculations and what was the other calculations we did? No, I think that's pretty much it. Just heat loads, really.
Fan static calcs, maybe?
Oh, fan statics, yeah.
Yeah, okay.
But like very isolated tasks, and that was all that was needed on that particular project. So I haven't really seen like a project in its entirety from like an engineering perspective. So I don't know if like you could cover anything
as well. Yeah.
Yeah. Something that Jellen's working on,
Yeah, that's fine. That's good. I find that probably the best thing. The more you talk about things and you start to look at drawings, then things come out that become important, and there might be things on your drawings that I could recommend, or that might be missing, that might be needed, such as dampers, and then we can talk about the acoustics and the vibration isolation of fans or fan coil units if it's needed. So looking at drawings and talking about them is always very useful.
Yep, definitely.
So do you want to do that next time? Just bring up one of your jobs and basically you can lead us off, Jess, on the drawing and tell us about the job, which is good for you too, to show your understanding of what the project is. And then we can have a look at the drawings and talk through it.
Yeah, I mean, the job I'm working on at the moment doesn't really, it's very like concept level at the moment. It's almost consulting level. So I don't really have drawings per se. I've got some very basic high level markups.
Sorry, if I can just interrupt you there. So you've got consultant drawings, have you?
Like we are basically the consultants on this particular job.
Oh, so you've got schematic. The
schematics
that we've done.
Yeah, exactly. Like just like line diagrams.
Oh well,
there's not much to it, but
still probably relevant to talk about
yeah,
when that's developed further, the things that you need to be aware of.
Yeah, that'll definitely be good.
Hmm.
Happy to do that.
Well, you want to do that next time then?
Yep, sure. Provided
Okay.
I can speak next
Yeah.
week.
Well, you got 2 weeks.
Yeah, that's true.
I've cancelled the next week, next week's meeting. So the next one will be in 2 weeks' time. So hopefully you'll be all right by then.
Yeah,
And
that'll be
you
fine.
won't have to shout too much because Collingwood's out of it now, so you can relax.
Thanks for reminding me.
Well, my team's out of it too, so I'm finished for the year. So I've
Who's
got to hope we can do better next year now.
Yeah.
who's still
Well,
in it? What teams?
Um,